So a very good morning. I'll be just adding one single slide of our roadmap for RISC-V, and how much time I have for this presentation. Thank you very, very much for this excellent opportunity to present before the RISC-V interest group. So what I put in front of you, ladies and gentlemen, is the RISC-V initiative at India, what we are today and what we plan for the next 3 years. And that is what is the RISC-V roadmap. Before going into this roadmap in great detail, I would like to basically tell you about what is happening in the RISC-V ecosystem in India. Around 2013, we started the RISC-V effort when it was at its very, very nascent stage. Berkeley, MIT, and IIT Madras at that point of time started making microarchitectures. As you all know, RISC-V is an open source instruction set architecture. And the implementation of that instruction set architecture is left to the different teams. And we started this implementation as early as 2013. 4 years we spent to come out with different varieties of architecture, at least the definition of those architectures that we freezed around 2017, wherein we decided that we will follow some of the contemporary processor company route, like we will make a family of microprocessors. The family of microprocessors that can fit into very, very small devices, the IoT or the embedded system devices, to some medium devices like the point of sale terminal or your small scale routers, and then to a little more higher end devices like laptop and mobile phones, and then very high-end devices like the cloud-based server system. So we have a very grand plan of trying to make multiple such cores, multiple such SoCs based on the RISC-V. With this, we started around 2017. We had our first chip, which was done at a 22 nanometer fabrication facility of Intel, wherein we got what we call as a controller class, the mid-class in-order pipeline chip that was made. So as you see on the leftmost side of this particular presentation slide, you see the RISC-V, which is a 64-bit, and this was taped in 2017, and the chip came out in 2018. And this was a single core of 350 megahertz. It was targeted for a very, very low power design, and this was fabricated in 22 nanometer. Subsequently, we also want to see how this will fare in a larger node. And India has a facility for 180 nanometer, and we wanted to develop the entire ecosystem within India. And so we made the same design, the RISC-V design, as a 64-bit core, again in 2018, which was a single core in 180 nanometer, and that was actually taped out at 70 megahertz at 180 nanometer, and that also worked. These two are initial first-time silicon success, and we were able to boot Linux. We were able to boot a series of what you call as the operating systems. We were able to run large-scale benchmarks on this, especially the floating point intensive benchmarks, and then certain RISC-V specific benchmarks like Paranoia, which we are able to run very successfully on it. Around 2020, we also had one more tape out, a very successful tape out, the E class, which is called Maushik. This is a single core, 100 megahertz on 180 nanometer, and it is a 32-bit core. And this is basically for the embedded class and IoT class of systems. So 3 successful silicon in the RISC-V by 2020 was actually gave us a lot more confidence to start investigating more on the RISC-V. and invest more on the RISC-V roadmap. So around 2021, when the pandemic was in full flow at the part of the world, we did open up a microprocessor challenge, wherein we said that we will open up these RISC-V cores, and we encouraged people in India to start developing applications which would be of good societal and economic impact for the country. While we were developing the same, there was another core that was also coming up. These three cores that you see on the left-hand side are the Shakti class of cores, and then we also have another class of cores called the Vega class of cores. Again, they are another family of RISC-V processors. So two parallel efforts are there now currently in India, and we started this grand microprocessor challenge, wherein we had around 6,000 participants for this, and then the top 30 teams were shortlisted, and there we found that from health to agriculture to robotics to drones to other type of lot of sensing devices, whatnot, we saw many applications that were successfully done using the RISC-V processing system. Subsequently, we also developed the SDK, a software development kit. So the software development kit was used on these architectures, and many such applications were built and demonstrated. And that added a lot more of confidence in the role of RISC-V in the microprocessor market of India. And with that, powered by these success, we now announced, the government has now announced what we call as the DIRV program. This is Digital India RISC-V program. This was announced in April as a part of our Semicon 2022 event, which was a flagship event of Government of India. Government of India has come out with the semiconductor policy, which gives a $10 billion incentive and grant for developing semiconductor ecosystem in the country. So we started in the last week of April. The Semicon 2022 was conducted, and the DIRV program was also announced at that point of time. So now, as a country, India has now committed herself to the RISC-V as our national instruction set architecture, and we will be promoting RISC-V in its full form for many of our computational needs. So with this as a background, I am now very happy to go ahead and start explaining to the team, explaining to all of you what would be our next 3-year roadmap. Now, the RISC-V, as we are progressing, has now, as an instruction set architecture, has many features that we need to include. One set of features is, as all of you would have understood, there are many types of instructions and very many classes of instructions, which basically defines the core. So we have integer instructions, we have multiply add instructions, we have the floating point, double precision floating point, atomic instruction. So we have this RV, this phi, IMA, FD, etc. Now, every upgradation of the RISC-V, as you know, that RISC-V is an extensible architecture, it's an extensible instruction set architecture. So I can keep adding more instruction without breaking the current encoding of existing instructions. So that is a very important aspect for a growing ISA. Now, as we are seeing this, as the growth of this ISA, as we are seeing this ISA evolve, now we are seeing more and more instructions like the vector instructions are getting added, and more instructions are now coming into the RISC-V ecosystem. So this is one part of the entire ecosystem. The next thing that we are also looking at, in addition to this instruction set architecture, are the security features. Now, we strongly believe as a country that any device, whether it is going to be at the lowest end on IoT or an embedded system, or it is going to the cloud, should have inbuilt architectural features or micro-architectural features that address security. So in this context, if you look at the way the RISC-V ISA has evolved, the RISC-V currently works on 4 modes: the user mode, the hypervisor mode, the supervisor mode, and the machine mode. Or so to put the order correctly, it is the user mode, then comes the supervisor mode, then the hypervisor mode, and the machine mode. So this is how the architecture works. And the machine mode, which is the highest, most powerful mode, and then comes the hypervisor mode. So there are certain instructions that cannot be executed at the hypervisor mode, which can be executed only in the machine mode. So machine mode is the most powerful. It can do everything with the microarchitecture. Lesser power is the hypervisor, and then the supervisor, and then the user mode. So traditionally, this 4 mode of operation is very close to what other contemporary architectures also have. And these 4 modes, the origin of having these 4 modes actually evolves from the operating system and the compute stack, which actually wants a kernel and then a system layer and then the application layer. So the layered operating system has also been played a very important role in evolving at these modes. Now so the microarchitecture gives us these 4 modes of operation, and in addition, this also gives us privilege levels, which will allow us to enforce certain regulations in the access, etc. When the system is working in each of these modes. For example, we have something called physical memory protection. The physical memory protection actually can define segments of the memory address space, and for each address space we can assign certain privilege levels, and the microarchitecture takes care that only privileged access can happen to these levels. So the levels of operation, along with powered with things like the physical memory protection and certain privileged instructions, etc., essentially helps in a very, very robust implementation of certain security aspects. And that is where the whole software domain now becomes extremely important here. So our concentration in the DIR5 program will be to evolve architectures and software layers which will essentially lead to secure computing environment from the embedded devices to the overall our what we call as the supercomputing or the cloud-based high-performance computing system. So this is so what we have done. So one thing is the microarchitecture provides certain security features, but the most important thing is that the compilers and these application software should utilize these features in a very nice way, right? If they do not utilize this, then this basically the security that is envisaged by trying to have a ISA which is extremely conscious of security is completely lost unless we have a software environment which will basically look into and utilize these secure features and take it forward. So with this context, what we have done as a part of our effort in India is that we now have what we call as a separation kernel. A separation kernel that is part of the entire compute stack. What is a separation kernel? A separation kernel sits between the hardware and the operating system, and this separation kernel will now have the complete control of could look into every hardware software interactions, and we can put certain rules and regulations in the separation kernel so that no unauthorized access of resources happen from the software side. By this, I could have a completely unknown operating system, and I could have a relatively known but not fully known microarchitecture, but I could have a layer which is completely known, say even formally verified separation kernel, which can ensure certain access patterns are really followed, and certain all unauthorized access are completely thwarted. So this is something very, very important. So we have come out with a separation kernel called SecureWeave. It is by one of our startups in India, which is a completely indigenous one, and that separation kernel will now execute in the hypervisor mode. So there is a machine mode in which the system boots, then it switches on to a hypervisor mode where the separation kernel works, and the operating system will be now loaded on top of the separation kernel, and the operating system will work as a para-virtualized container. It will be one para-virtualized part which will work on top of this the separation kernel, and the operating system will work in the supervisor and the user mode, application mode. So by this, what happens is that the hypervisor mode, supervisor and the user mode, application mode. So by doing this, what happens is the separation kernel, which is at the hypervisor, is completely protected, and every interaction that comes from the higher layers like the supervisor mode and the user mode will pass through this hypervisor before reaching the actual hardware, and that can ensure lot more of security. So this is one very important thing that we have done. So currently we have a course, the C class and the we call I class, which is I class is the super scalar core, which now will be sort of the next supercomputing core, the core that will be used for the supercomputing, so sort of SOCs. It will be used for the mobile or laptop type of course that we are trying to plan in this entire RISC-V ecosystem. Now, let me just look at the roadmap now. We are currently around June 2022 as of today, and what we have on the left-hand side, we have 3 chips that we have proved that it will work. We have also now the 4th chip that has come, the Tejas 32, which is again a single core 100 megahertz 130 nanometer chip, and all these the Tejas 32 is now can be actually commercially sold now. So that is the 4th chip that has come. Now we also have a bunch of peripherals that we have done, like the low speed peripherals like SPI, UART, I2C. These are also available. Then the high speed peripherals like USB, MIPI, HDMI can be sourced. We also have several hardware level security features like crypto accelerators, true random number generators, one-time programmable memory, etc. Here. So this is what we have now, and all that the Shakti program is basically working at. These Shakti cores are part of an open source ecosystem. So you can, and we develop these cores in a language called BlueSpec, which is also now open source. BlueSpec is a very interesting hardware definition language. We have been using it for last 15 years now, and that essentially the 3 first-time silicon success that we had got, the Rice Creek, the Maushik, the Remo, and now Tejas, the 4 successes we have got, crucially depends upon the BlueSpec, which is a very, very powerful language, which automatically takes care of many things that can go wrong in a chip design, including race conditions, etc. And that is something has been a very important ingredient to the success of this program. So what we look forward is the next chip that would come are 2 chips. which is the Tejas 64-bit single core that we are envisaging around another couple of months. And then we are also looking at the 2023, where we are looking at the Shakti 64-bit core with 1.2 gigahertz, 28 nanometer. That is something that we will look at for many of the point of sale terminal or many of the access control systems, where you need sufficiently large encryption algorithms, etc., to be run. And that is what we are looking at. And it will be a secure Shakti, secure in the sense that it will have the hypervisor, etc. And similarly, there is a Dhruv 64, which is a dual core 1 gigahertz that they are planning somewhere in 2023. Now, going forward from in the 2023-2024 time frame, that year, we are looking at the Shakti I class, which will be a single core 2 gigahertz at 10 nanometer, and a Secure Shakti C class, which will be a quad core 1.2 to 1.5 gigahertz and 28 nanometer. And by the end of 2024, we really want the Dhanush 64-bit, which is a quad core 1.2 gigahertz at 28 nanometer. So we are basically looking at these three in the 2024 project. By 24-25 is where we go into the high performance domain, where we are looking at Shakti Big Little 64-bit, where M big cores and N small little cores. The big cores would be the I class, which will be a sort of which is multi 12 to 14 stage 4 instruction wide dispatch type of an architecture, which will be as popular as some of the as powerful as some of the contemporary architecture. We are also looking at Dhanush 64 plus 64-bit, which will be a quad core 2 gigahertz at 16-14 nanometer. And what we are looking at by 2025 is the Parashakti, which is a 64-bit server HPC class of RISC-V processor, RISC-V SoC, which will be at 7 or 5 nanometers. So these are all our complete roadmap, where we are looking at multiple small devices to a very large device. In addition, we have several startup companies who are looking at taking this open source course and trying to build certain SoCs which fits their need. For example, some startup companies need only the instruction and atomic instructions. They don't need floating point. So they can very quickly customize this course and take it forward. The other interesting thing about the open source Shakti development is that the Shakti cores are highly parameterized. For example, the 32-bit to 64-bit transition is only changing certain header files with certain values of this 32 or 64-bit. So we just go and change certain flags, and then we get a 32-bit core. If we change some flags, we get a 64-bit core. And so we have exploited the parameterizability of BlueSpec to its full extent to generate these cores. Now, what we look forward to the international stuff, that international relationship, specifically with countries like Japan, is that now we have these open cores. We also have certain silicon proof for this open cores. It's not that it has just an FPGA or a simulation proof. We have made silicon, we have made working silicon with these cores. Now we are very, very open to interact with multiple industries abroad, including Japan and Korea and all, to basically see how we can have a relationship with your industry there. And we are looking at several design wins using these open source Shakti processor. One of the interesting thing is that the entire thing is open source, and it is also released in the BSD license. So the point here is that you can take the core, you can do whatever you want with that core, and you need not tell us back what you have done with that core. What we are just looking for an acknowledgement saying that yes, it's a variant of the Shakti core, and that is what the maximum that we need. And we believe that this will democratize. This is a Linux model. There is a mother version of the Linux, and then there are several other commercial versions of the Linux which derived themselves from the mother version, like the Red Hat, the SUSE, the Debian, etc. And like that, the startup can take this mother Shakti, and then they can basically make multiple designs out of that. And the only acknowledgement we need is that the Shakti core is the base that they have used. So this is the democratization that we are looking for. Number one. So we are inviting companies and industry to please come and interact with us and make use of this. And we are very excited to have a jointly developed Shakti-based product which you can basically take forward and sell. So, and we have also made infrastructure ecosystem within our institutions here, which will support. For example, you come, you want one Shakti stuff, and then you need some changes. That we have a support ecosystem which will help you to change it for you and customize for you. So we have a very good, very vibrant startup ecosystem which can basically take the Shakti core here and make it suitable for you. And this is how you can engage with our RISC-V based startups, and that is something which is important here. The other thing that we are also looking for is the fab access. So we are making these open source design. All these designs will essentially need to be validated. So if there are fabs which are ready to interact with us, and we can make certain test chips which can further be used. For example, we are very interested in setting up a RISC-V flow, a fab-specific RISC-V flow, so that anybody who wants to basically start using the Shakti or the Vega processor, now there can be a fab-specific flow that we can set up so that they could come and quickly utilize this and make out a chip. So we want to, from the day that an idea comes for making a chip, we want to very quickly see that the chip is actually manufactured. So from concept to silicon, we want a very fast flow, and that is what we want to enable. The other thing is, of course, we need a lot of IPs. The IPs are the peripheral IPs, like the USB, MIPI, HDMI, etc. So if there are people who are developing these IPs and they want to test these IPs, they want to silicon-proof these IPs, they can actually come and start building a RISC-V ecosystem with us, where a chip can go with those IPs. And once it is proved to be working properly, that essentially gives them a silicon-proof to improve their market. So all these type of very interesting relationships are possible. And as the chief architect of DIRFI for India, I take this opportunity to welcome the entire world to start interacting with us, and we open up and let us see what best we can do in this big democratization of computing hardware. Thank you very much for this opportunity. I think I'm touched the 25 minutes. Now I am open to questions. I'll keep the slide as it is so that people can ask questions also. Thank you very much.